How's it going, AS Math? It's Mr. Knight, and this is our last lesson for this week. We're going to actually look at the displacement time graphs and figure out how to solve some of those problems. So to kick us off, looking at this graph right here, what could this displacement time graph below represent in real life? I want you to talk to a partner for about 2 minutes and be ready to share out. I'm expecting a lot of different answers. And go. All right, we're back. So, I'm sure we heard a lot of cool things. There's really not a lot of wrong answers for it as long as you are consistent with it, but there are some things we need to look at it. By the way, I was actually inspired by one of our students, Emily McNiven, to make this right here. So, let me explain. This is Emily as soon as her first hour ends. As soon as it ends, she starts walking towards my class at a constant rate. Takes her about 100 seconds to go 200 meters, right? And then as soon as she gets to her seat in my class, she stops moving because it is officially nap time. So she is going to sleep, 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 sleep. And then right about here, this is where the bell rings. And she kind of wakes up and she's kind of a little tired, a little sluggish, but then she starts kind of picking up the pace towards her next class. And then she gets back to her third hour, and then she falls asleep again. It is nap time once again. All right. So I use Emily's nap time in class as inspiration for this. But again, there weren't really wrong answers. So let's take a look at this guy. There are some features with this graph that we definitely want to discuss. Stage 1. Yeah, why am I saying stage 1? Well, we can break this graph up into different stages because, well, there's different things going on at different times, really, okay? So you could say stage 1 is this part right here where we have a straight line. Well, a straight line indicates a constant speed. We saw with our displacement time graphs for our lab that the slope of this guy is going to be our speed or our velocity. So if it's a straight line, then it's a constant speed. It's a constant speed, and the constant speed of that guy would end up being 2 meters per second. Okay? We can also look at stage 2, right? This horizontal line that's going straight across. So it's also a straight line, but there's really no rate of change. There's no slope with that guy. The slope's 0. So she, in that case, was stationary. She was napping. And so the velocity of her was 0. And our displacement didn't change as a result, as you can see. Let's kind of keep this guy on the side. And let's look at stage 3. So if this is stage 1, whoops. Let's kind of zoom out a little bit. Okay. If this was stage 1 and this was stage 2, I'm going to call this where it starts curving up stage 3. Well, it's a curved line. So that actually means that the speed is not constant, it is changing, right? She starts off kind of sluggish, picks up the pace, and then she tapers off and decelerates, right? There is an acceleration going on here, right? So no acceleration here, no acceleration here, but there is definitely acceleration going on here. So you can represent that with curved lines, all right? This is where the Suvat equations will really be helpful when we're trying to determine what our shape of our graph is going to look like. And it's not going to be perfect, but we can make it pretty accurate, okay? Since this is displacement, though, and not distance, we can have negative measurements for s. I'm not restricted to quadrant 1 on my coordinate plane. I, in fact, can have a graph that might look something like this, right? You start off being positive, maybe it's nap time, and then I guess you almost teleport or you are the Flash all of a sudden because you just speed in the negative direction. And now you're in the negative direction of where you started, right? And then you take another nap, and then you take a brisk walk back to your starting position, all in 150 seconds, okay? So you can have negative measurements for these things, and we got to keep that in mind as well. Let's move on, and let's actually see an example problem. Now, before you write all of this down, because you guys are crazy and you want to get all the notes, I get it, do not. Just refer to this page in your books. I'm going to pause it probably in real life and give you a chance to do that. Go to exercise 1D on page 16. It's the worked example you'll see there. So you can just follow along, and when you're taking your notes, you can just kind of get the gist and just write down how the process works. Okay? Less writing for you. Well, same writing for me, okay? Try to make your lives easier. So this is an example of sketching this displacement time graph. Let's take a look. So a racing car passes the finish line of a race moving at a constant velocity of 60 meters per second. And after 5 seconds, it starts decelerating at 3 meters per second squared until finally coming to rest. We need to sketch the displacement and time graph. So let's break this up into stages once again. Okay? I'm not going to graph anything yet because I don't really know what it's going to look like. I need an idea. Well, I do know that the first stage is really this racing car passing the finish line, and it's moving at a velocity of 60 meters per second. Okay, that's what it's doing right off the bat. So I can call T1 my first stage time, V is my 60 meters per second, and well, I need to find my displacement. Okay, so it says after 5 seconds it starts to decelerate. So it's really going at this constant speed for 5 seconds. So we actually do have the time for this first stage, and we're going to utilize this equation. This comes from the fact that your velocity is equal to your distance or your displacement over time. So I just rearrange the equation, okay? And so we can solve for displacement that way. So what I ended up doing was I ended up solving it out, okay? So when I did 60 times 5, I ended up getting 300 meters for my displacement. So again, if it's displacement versus time, here's my y-coordinate, here's my x-coordinate, and I can do it like this. 5 seconds is my x, my y is 300, and I know it's a constant velocity. Constant velocity. It's a straight line. Just a straight line like y equals mx plus b. And the first stage is done. The second stage, this is where it starts to decelerate. So I know it's decelerating at 3 meters per second, and since it's decelerating, it's negative. I know my initial velocity is actually this guy right here, because this is stage 2. I'm starting with that speed until I eventually come to rest, which will make my final velocity 0. I need to find my second stage time, and as a result, I need to solve for my second displacement. You know, again, get that x, y, and see what this is going to look like. Since it's accelerating, what do you guys think? Is this guy going to be a straight line? Is it going to be curvy? Is it going to be just flat? Like, what is it going to be? Go ahead and think about it now. All right. So because it's accelerating or decelerating, it is going to be kind of a curve like we saw earlier with Emily waking up and realizing she's going to be late for class, right? So we have that guy right there. So let's kind of move on with this idea a little bit more. If we want to find, and we do want to find T2 and S2, this is what we can do. We can utilize our Suvat equations. I ended up using V equals U plus AT subscript 2. This is my time 2. And so I put 0 in for V, 60 for my initial, and negative 3 for my A. I solve for T squared. I find that it is 20 seconds. Okay? Now I can find my displacement. I actually didn't need to solve for the T first to find my displacement because you can use that V squared equals U squared plus 2AS equation, this guy right here, in order to find the displacement. And I recommend doing that just because, like, it doesn't rely on time. So it's we have the information that we need already. So we're going to get the exact displacement no matter what. So if we go ahead, plug in some values, I get 0 equals 60 squared plus 2 times negative 3, S subscript 2, negative 3600, because this is 3600 and I subtract it over. I get negative 6s2, divide both sides by negative 6, I get 600 meters for s2. Now, this is the second stage. So it's not like I'm now just going to go from here to 600, or sorry, I'm not going to go from here to 600 right here. This is stage 2. So I'm not just going from here to here. I'm actually adding that 600 to my original 300. So I'm actually at 900 meters. Same thing with the time. I got to add the 20 seconds. I'm actually at 25 seconds. Let's see what that looks like with our final product right here. Okay? So if I'm adding this guy there, this is going to be at 900. This is going to be at about 25. And so I know that point is going to be right about there. And again, you're not looking for perfection here. But we do know it's going to be curvy because it's decelerating. So as it kind of tapers off, it's going to slowly decelerate right there. And that, ladies and gentlemen, is our displacement time graph for this example. Okay? And that's all we needed to do. Not too bad, not too bad. Just keep that in mind with that first example I showed. Okay? Well, let's actually see